Okay, good morning everybody. Today is our 10th lecture and the topic is approximate Riemann solvers, HLL and HLLC methods. First of all, about the previous lecture. So the previous lecture was about the construction of the solution of the Riemann problem. We considered the Riemann problem for the order equations. It means that we considered the Cauchy problem or initial value problem with the discontinuity in the initial data. So for x less than 0, we have conservative variables vector UL, and for x greater than 0, we have a conservative variables vector UR. And in general, there is no relationship between these two vectors at all. And the question is what the solution will be. What is the structure of the solution will be. And we discussed that there are 4 possible configurations of the solution. So we discussed that the solution of this problem should be self-similar because there are no parameters with the dimension of time or space, and only one of these 4 configurations is possible. So the first one is when we have one shock wave propagating to the right relative to contact surface or contact discontinuity, and one shock propagating to the left relative to contact discontinuity. The second option is when we have a shock wave propagating to the right and the reflection wave propagating to the left. The third option is quite contrary, when we have a reflection wave propagating to the right and the shock wave propagating to the left. And the fourth configuration with 2 reflection waves. And so this dashed line corresponds to contact surface. And so this is only the schematic. All these waves can, falls into different regions. For example, they can be in whole for the region x is greater than 0 or x is less than 0 and so on. And so during previous lectures, we discussed the relationships so what is the relationship between parameters across the shock wave, contact discontinuity? What are the parameters inside the reflection wave? And so when we obtained all these necessary relationships, we analyzed the solution of the Riemann problem using so-called PV diagram. So this is the diagram in space of velocity and pressure. And here it's possible to place points corresponds to states of gas to the right of initial discontinuity and all possible states of gas to the left of initial discontinuity. And so this, for example, we carried out, we considered the solution of Riemann problem on the example of so-called SOTS problem or SOTS shock tube problem. And Gary Sot is a researcher who proposed these parameters of this Riemann problem, and nowadays they are widely used for verification, validation of implementation of a numerical method or software. So I'd like to remind you briefly, right? So here we have this point E. This point E corresponds to the right state, and point B corresponds to the left state. And so this red curve is all possible states for the gas to the right of discontinuity after propagation of any shock wave. And this blue curve is Poisson adiabatic curve corresponding to the all reflection states for the right gas. And the same can be done for the gas to the left of discontinuity, and we can find the intersection point, and it will correspond to parameters at the contact surface, at the contact discontinuity. So these PC and VC values, they are VC and PC, the coordinates of this S point at this diagram. And if you know these parameters, PC and VC, velocity and pressure across the contact surface, it's possible to find the rest quantities, namely the velocity of shock wave, velocities of or parameters of this boundary characteristics of the refraction wave, and so on and so forth. So actually, it's possible to solve completely the Riemann problem. And this is the example, the solution of this SOTS problem at some time instant. So this is the density distribution. So the shock wave, contact wave, and the refraction wave. So we discussed all these topics. So it was a bit theoretically, and maybe not so easy, but this is the foundation of actually computational gas dynamics. The numerical method based on this consideration is called a Godunov method. So how can we use these results in numerical simulations? So Godunov-flux finite-volume. Suppose we want to use a finite-volume approach. So here n+1 is a grid function, conservative variables vector. So as usual, m is spatial index, n is time index, tau is time step, h is the size of our computational cell, and fm plus 1/2 n is the numerical flux through this h, and fm minus 1/2 n is numerical flux through this h. And this formula shows how can we evolve from nth time layer to n plus 1 time layer using this finite volume method. And the question is how to compute this numerical flux f. And generally speaking, for the first order methods, we discussed it, the fm plus 1/2 n is some function of two states, umn and um plus 1n. So if you want to compute numerical flux through this h, it should be some function of these two states, to the left and to the right of the h of the computational cell. And the idea of the Godunov method is as follows. We should compute the exact solution of the Riemann problem for these two states, and then put this exact solution into the flux. So f here is just the flux rho v squared plus p, rho e plus pu, and we put the exact solution of the Riemann problem into this flux. So the numerical flux is very easy. The problem is how to get this Riemann problem solution. But if you know it, we just compute the flux using these parameters. And it means that at each boundary of our computational cell, we should solve this Riemann problem. So for the moment, we can just forget about our numerical solution, and we can think of this problem as Cauchy problem for the Euler equations. So suppose we have this initial discontinuity and parameters to the left and to the right. And suppose we know how to solve this problem. And for example, this is just the schematic for the parameters to the left and to the right. We have this configuration: shock wave propagating to the right, contact surface, and refraction wave. And we should define in which region this h of our computational cell falls. For example, here it's situated here. It means that we should take parameters corresponding to this state, because so here parameters are constant between the shock wave and contact discontinuity, and here the parameters are constant between contact wave and this characteristic of the refraction wave. So we know these parameters. We take them and put them into the flux, and that's the idea of the Godunov method. At another h of our computational cell, we do the same thing, but now we consider the solution of the Riemann problem for this state and for this state. And generally speaking, there is no relationship between the solutions of these two problems. So this is only, again, the sketch for sure in real computation. The parameters in three neighboring cells, they should not differ significantly. Otherwise, so something goes wrong. For sure, the solution here and here will be or must be, close to each other. So this is just the sketch. But you can have any configuration that we discussed previously. For example, the shock wave propagating to the left, contact wave propagating to the left, and the refraction wave, and for example, your h x m plus 1/2 can be inside this refraction fan. And again, we discussed how to compute the parameters if our h is inside this refraction fan. And that's it. So we take this solution of the Riemann problem and put it into flux, and then we get the flux through the right h of our computational cell. And this picture also illustrates that our time step tau should not be arbitrarily. For example, if it will be too big, for example, it means that it should be small enough because we can have a situation, for example, when this shock wave at Tn plus 1 can reach the neighboring cell, that's bad, or we should, so the situation when characteristics intersect is also bad. In this case, we can get the numerical instability. So it means that all this wave structure should be compact. It should be just near our H, and it can be ensured using small enough time step. I mean that this picture also illustrates the principles of CFL criterion for the stability. This is how can we use the results from our previous lecture in numerical simulations. This method is called exact Riemann solver. So this term solver, so it used to be slang, but nowadays it's a valid terminology for numerical solution of gas dynamic equations. So solver means both the numerical method and your code and software, everything that is based. So if your code or method looks like this one, finite volume method with numerical flux that is computed using exact solution of the Riemann problem, it is called exact Riemann problem. If you have an exact Riemann problem, it means that we also have approximate Riemann solvers. So all solvers which are based on finite volume method, but with not exact solution of the Riemann problem, but with some approximate approach how to get this numerical flux, they are all called approximate Riemann solvers. And they can be very different. So for example, there are a number of approximate solvers that do not compute all the states. So you can see that Godunov method is based on getting these constant states separated by characteristic lines. For example, constant state here, constant state here, here, and here. And so one of the idea is, so it's the idea of methods of HLL and HLLC, it's the topic of our today's lecture, is to approximate somehow these constant states. At the same time, there are approximate Riemann solvers that do not compute these intermediate states. They estimate the flux, numerical flux itself. For example, we already discussed this Courant-Jackson flux finite volume method. So you can choose this function of states to the left and to the right of the H of our computational cell in this form. And actually, I explained to you how to get this formula. We derived it. We started from Courant-Jackson numerical scheme for linear direction equation. Then we generalized it for linear system of hyperbolic equations, and then for nonlinear system of hyperbolic equations. And it will look like this one. And so we need to estimate somehow this matrix omega r mod lambda omega l at the edge of our computational cell. And there are actually a lot of methods here. It depends on how can we choose this matrix. So Roy scheme, Lax-Friedrich scheme, Rusanov scheme. So it's the general notation for all of them, and it depends on how can we choose this matrix. In the lecture, I will use the following notation. So f of umn is f the capital Mn. So f is flux in our initial problem, and so fmn means that we put the grid function conservative variable in this flux f. And it looks like the formulas are totally different, right? So we try to solve the same problem, but there is this way. How can we do that? Compute this all states, so solve this, know what is shock wave or refraction wave, so it looks very, very difficult, right? And here we can know nothing about the structure, so we may know nothing about shock waves, or contact discontinuities and so on. And you may think that these formulas are totally different and they will produce different results. But interestingly, they're very close to each other. So you can take this SOTS shock tube problem that we discussed previously and compute it using Godunov method and compute it using Courant-Jackson method, and you will see that actually the results are the same, so almost the same. You cannot make a distinction by eye, so they look like the same. And even more, you can see that in some sense Courant-Jackson method is better, because these blue rectangulars, they correspond to Godunov method. For example, you can see here, so this is a specific feature of the matter. small overshooting, so it's called entropy glitch. So although the Godunov method is entropy satisfying, so it's very physically relevant method. Anyway, on the numerical level, you can have the violation of second law of thermodynamics, and it results in this small glitch. Actually, this amplitude, so this overshooting becomes smaller and smaller with mesh refinement. But anyway, for example, Kurzak Sonoris doesn't have this feature. It means that actually, so this slide illustrates that actually, all methods, all numerical fluxes, they have their pros and cons, their advantages and disadvantages. And that is why if you write your software, your codes, usually you should have a set of different numerical fluxes, and you should use one or another depending on the problem under consideration. And that is why you should be an expert in flows, types of flows and problems which you would like to solve, and you should choose the appropriate approach to solve your problem. Exactly, approximate Riemann solvers. So the method of Godunov and its high-order extension, so we move towards high-order extension. So everything that we're discussing now, so it's about first-order methods. So that's very important, but anyway, nowadays people try to use high-order methods. Require the solution of the Riemann problem. In a practical computation, this is solved billions of times, making the Riemann problem solution process the single most demanding task in the numerical method. So let's discuss the pros and cons of the Godunov method. The most problem is that you should solve this problem at each age of your computational cell. And if you have billions, hundreds of billions of your computational cells, so this is very frequently used operation in your code, and the computational cost become too high. An iterative procedure is always involved, and the associated computational effort may not always be justified. So that is why, even if you understand how to use this Godunov method, maybe it's not appropriate for us. Maybe we do not have the suitable computational facilities to do the necessary simulations. That is why people developed a lot of approximate Riemann solvers. So one of problems with Godunov method, one of the disadvantages is the computational cost. This effort may increase dramatically by equation of state or of complicated algebraic form, or by the complexity of the particular system of equations being solved, or both. So the second problem is that, actually I mentioned that, but if you will check carefully, you will see that everything here is valid only for the ideal gas equation of state. P rho gamma minus 1, where gamma is the specific heat ratio or adiabatic index. And actually all these formulas that we derived here for shock waves or refraction waves, they were all for ideal gas. And in reality, and even today I will show you an example, in reality, very often you need to use more complex equation of state. And if you need to use more complex equation of state, it is known how to write Godunov method for so-called Stephen gas equation of state. But it's actually the most general equation of state that can be used to write the Godunov method. It means that if you have some complex equation of state, you need locally approximate your equation of state using formulas for which the Godunov method is known, and then locally apply the Godunov method. And so you have this procedure working with the equation of state, interpolation of states, and so on and so forth. So the second problem is that, for example, Godunov method is not able, so you cannot use it straightforward with the complex equation of states. So computational cost, the problems with the complex equation of states, approximateness. So that's actually two main problems. And the third is that even although it's entropy satisfying, still you have some numerical features of your Godunov method. So it's not the ideal method, even from point of view the results. Even if we forget about computational costs and we won't consider only ideal gas equation of state, even in this case, for some problems, Godunov-flux is not good. It does not provide good results, accurate results, physical results, physically relevant results. That is why approximate non-iterative solutions. So the problem is here that we have iterations, maybe not many iterations, but it depends on the difficulty of your flux. Non-iterative solutions have the potential to provide the necessary items of information for numerical purposes. So people try to develop approximate solvers without iterations. There are essentially two ways of extracting approximate information from the solution of the Riemann problem to be used in Godunov-type methods. One approach is to find an approximation to the numerical flux employed in the numerical method. So this is approach corresponding to Courant-Jackson numerical method. We do not, we don't, build these states and so on. We just provide some, provide numerical flux as it is. And the second approach is to find an approximation to a state and then evaluate the physical flux function at this state. So just different strategies how to build the approximate Riemann solvers. And actually, we discussed previously the first one. It corresponds to Courant-Jackson numerical scheme. And today we would like to discuss the second approach. So this is from book Toro book. Actually, today's lecture is based on materials from Toro book. It's explained excellent in there. You can see that I use different books, different sources for different topics because I think that so they explained in a better way in different sources. So that's why I recommend you different literature. HLL. What does it mean? HLL. So it's the abbreviation Harten-Lax-van Leer. So three researchers, three scientists, and this method is named after their names. They published it in this SIM review journal in 1983. Actually, it's not so, and so they explain the idea, but actually, as in many cases, this paper does not contain the ultimate formulas that can be that you can take and implement in your code. So that's not very easy to read this paper. And actually, in subsequent papers by different authors, they provided all the necessary formulas. And for example, in Toro book, you can find the final formulas that can be implemented in code. So the first author, Amiram Harten, he was an American and Israeli applied mathematician, and he made fundamental contributions to the development of high-resolution schemes for the solution of hyperbolic partial differential equations. And among other contributions, he developed the total variation diminishing TVD scheme, which gives an installation-free solution for flow with shock. So you can see that this science is very young, right? So the fundamental results in this field were obtained, just 30 years ago or something like that, and 40 years ago. I'd like to mention here two papers. So the first one is about the HLL scheme. For sure, they did not name the HLL at that time, so because it's not very convenient. And so this is a paper about that. So the second author is Peter Lax. So we have already discussed Lax equivalent theorem. It is here. And the third one is Bram van Leer. I will also explain who is it later. And the second paper, very, very important paper of maybe one of the most important of Harten, is high-resolution schemes with hyperbolic conservation laws. It is this paper in which he introduced so-called TVD schemes. We also discuss the concept of nonlinear TVD stability in next lectures, and also the schemes that can be built using this stability criterion. For example, so in this paper, we consider numerical approximations to weak solutions of the initial value problem for hyperbolic system conservation laws. Okay, here use the column vector of m unknowns and f is flux. And so equation is called hyperbolic if eigenvalues of the Jacobian matrix are real and set of eigenvectors is complete. So there are a number of them. So we can see that you're qualified enough to start reading this paper. At least the first page, you can understand everything that is written here. After that, he introduced some entropy function, and so things becomes more difficult. But actually, so I tried to explain you the main things. So if it is necessary for you to work deeper in this field, so I hope that you will be qualified enough to read even these original papers, and I recommend you to read these original papers because you can know a lot of important things from there. So the first author of the HLL. So the first author is Harten, Amiram Harten. The second author is Lax, and the third one is Bram van Leer. So it's also very important. So he is still emeritus professor in the University of Michigan in the United States, but actually he is from Netherlands. He was a doctoral student in astrophysics when he got interested in CFD for the sake of solving cosmic flow problems. And his first major result in CFD was the formulation of the upwind numerical flux function for a hyperbolic system of conservation laws. So it is believed that in his PhD thesis in 1970, he derived this formula, right? So this is this formula. So during our lectures, I explained to you how to do it. I'm not sure that he used the same approach in his PhD thesis. I didn't check that. But actually, it is believed today that he was actually the first one of the first who introduced this matrix, mod A matrix, in gas dynamics. So it's a matrix. It's the product of omega r mod lambda omega l. So he explain the importance of this structure of your hyperbolic problem. And actually, it was 1970s at that time in Soviet Union as well. So these approaches were developed, but it was not less than 10 years before Rowe first presented his much used averaging formulas. So we also discussed that, for example, so the specific numerical flux depends on the choice of this matrix mod A. For example, you can use Rowe averaging procedure or Lax-Friedrichs approach and so on and so forth. So this is the first contribution, is believed so, of Van Leer. And he is also famous for his 5-part article series towards the ultimate conservative difference schemes. So he published 5 papers with the same title, but with numbers 1, 2, 3, 4, 5, in which he established the theory of so-called Muscle scheme, monotone upwind scheme for conservation law. One of our lecture will be about these muscle schemes. So there are muscle schemes, TVD schemes, so the different approaches how to build non-oscillating high-resolution methods, how to overcome difficulties and restrictions of Godunov theorem. We'll also discuss, so what does it mean? So according to the Godunov theorem, you are not able to build a linear scheme, monotone linear scheme with accuracy greater than 1. And so if you want to have higher schemes, you should somehow resolve it. Otherwise, you will get the physical oscillations. Okay, this is some historical background. So let's discuss what does it mean. So the idea of the Harten-Lax-van Leer method. So once again, this is the original paper, but as I told, so it does not contain all the formulas. Later in paper of Davis, for example, he provided a number of, the problem is how to compute the speed of propagation of your disturbances. And so he provided the necessary results. And for example, in the book of Torah, you can find the full description of this numerical method. So this is so first of all, let's analyze the solution of the Riemann problem. So we start not with the numerical method, but with some preliminary considerations. So this picture illustrates the structure of the exact solution of the Riemann problem. So suppose we have the right state, we have left state, and in many books, even in 1D, people consider flows with 3 components of velocity, UR, VR, and WR. That's important because it relates to the development of multidimensional finite-volume methods. We will also discuss this issue. But the problem is that, if you will try to use results from 1D in multi-D, you should somehow introduce the second and third tangential components of your velocity. So anyway, so this is the general structure of the exact solution of the Riemann problem, from Torah book actually. So this is the schematic representation of the right wave and the left wave. So we have 2 characteristics as a representation of, for example, we do not know what do we have, shock wave or refraction wave. But anyway, the right wave is associated with the eigenvalue u plus a, where here u is the velocity and a is the speed of sound, and the left wave is associated with eigenvector u minus a, and the contact wave is associated with eigenvalue u, so the motion of media as itself, and we have these two states to the left and to the right, and so this is the exact solution. And I believe I explained to you how to find all these states. It's possible. We know how to do that, but it's difficult. Suppose that we do not want to do that. And the idea is as follows. Let's just forget about this contact surface, and let's substitute these two states with some average states. So suppose we want to use two-wave approximation of the structure of the exact solution of the Riemann problem. So we know that should be some disturbance propagating to the right, to the left, and let it be. Let's estimate somehow these speeds and estimate the state here between these two characteristics, SL and SR. So they write following in in this paper of Harten-Lax-van Leer, they write that denoted by AL and AR, so the SL and SR, lower and upper bounds respectively for the smallest and largest signal velocity, calculated according to same algorithm. So these are estimates of minimum and maximum wave propagation speeds in the solution of the Riemann problem. So we do not want to know, so what do we have, either a shock wave or a refraction wave. We need only estimations of minimum and maximum wave propagation speeds. So in this solver, two waves separate three states with constant parameters. We can expect even at this stage that such an approach will meet some difficulties. For example, if we cancel the contact surface, it means that we can expect lower accuracy in capturing contact discontinuities, and that's true. I will show a number of numerical examples in which you will see that indeed the resolution of contact discontinuities is very bad, very poor. And also you can meet some difficulties when applied to multidimensional case, because I try to explain to you even now that in multi-D, in 2D or 3D, sometimes you need information about your contact surface because it helps us to choose the relevant tangential components of our velocities. So we can expect also some difficulties in using this approach in 2D or 3D, in multidimensional cases. But anyway, so this is the idea. Let's implement this idea. So first of all, I'd like to remind you the notation. So once again, we work with conservative conservation form of Euler equations, conservative variables, flux vector. So and now once again we work with the Riemann problem. So now we try to obtain some consequences of the exact solution of Riemann problem. How can we do that? So it's not the computational cell, it's just the Riemann problem. So suppose we have the Riemann problem, left state, right state. Let us consider that the whole of the wave structure arising from the exact solution of the Riemann problem is contained in the control volume XL, XR, 0T. For example, let's choose some boundaries XL, XR, and let's choose some time instant T. And so suppose that all the this wave structure with shock waves or maybe refraction waves or whatever is inside this control volume. So it means that XL is less than TSL, where T is time, SL is the bounding characteristics. So it's once again. So what does it mean SL? SL is the minimum wave propagation speed, and SR is maximum wave propagation speed. Here we believe that we know them during this consideration, and after that I will provide you some estimations for this. So it's the misprint, it should be SR here. So where SL and SR are the fastest signals velocities perturbing the initial states, UL and UR respectively, and T is the chosen time. Okay. So the whole this wave structure should be inside this control volume. Then we want to apply integral form of conservation. So then we want to take this integral form of conservation loss and apply it to the control volume XL, XR, 0T. for many times we use this formula during our lectures. It's just Euler equations in the integral form. So, so usually this guy was here. It was the integral over from xl to xr, uxt minus ux0, and here in the right hand side we had integral from 0 to t, and the difference of fluxes through the boundaries of our control volume. So this is just integral form of Euler equations written to this control volume, right? Now let's evaluate all integrals here. So what does it mean? Integral from xl to xr of ux0. So ux0, it means that ux and t equals 0. So it's this. It corresponds to the axis t equals 0. But here we have our Riemann problem. So we know that here u equals ul, and here u equals ur. So it means that from xl to 0, ux0 equals ul, right? And for 0 to xr, ux0 equals ur. So that's the initial statement of our Riemann problem. Here our control volume, it contains the whole structure. So it means that at this h parameters are constant, and they correspond to the right state, ur. And at this h of our control volume, the parameters are also constant and then correspond to ul. So we can write that this f of uxlt is just f of ul, and this is just f of ur. Okay, and so all these parameters are constants. That is why, so this integral equals minus xl ul, this xr ur, this tf ul minus tf ur. So this condition is called the consistency condition. I will explain later why. Why is it called consistency condition? Okay, we integrated our function at t equals t the capital from xl to xr, and it can be expressed using these constants. Now we should work with this integral to the left-hand side. Integral from xl to xr uxt dx. Now we split the integral on the left-hand side into three integrals. Why three? Because we have this part, we have this part, and we have this part. The first part is integral from xl to tsl, the integral from tsl to tsr, and from tsr to xr. Here, uxt equals just ul because it's the left state, and here uxt equals xr ur because this is the right state, and here we do not know. So this guy we want to compute it. So what are we trying to do? We try to compute the average state in this region, that is this value, and evaluate the first and third term on the right hand side. So I explained how to do that. We obtain that this integral equals this integral equals to this one. We keep this one and the third part. And now we can put this integral back to our consistency condition. Comparing this equation with the consistency condition, or it means that we put it in the consistency condition, we get this equation, and then we can see that number of terms, they just cancel out because they exist in the left side and in the right hand side part of our equation, and we obtain this equation. So this is the integral from tsl to tsr of this function uxt. On division through by the length tsr minus sl, which is the width of the wave system, right? Of the solution of the Riemann problem between the slowest and fastest signals at time t, we have And it is so. This is this average state. That's the integral average. So this is the integral average of the exact solution of the Riemann problem between the slowest and fastest signals at time t. And so it's a constant because all these parameters are constant. We believe that. So once again, we do not know at the moment what does it mean SR and SL, but we consider these parameters to be constant. And so that is why this UHLL, so it's some constant. And so it's constant provided that the signal speeds SL and SR are known, and we denote UHLL. So it's the constant parameters here. Okay. The next. So what we would like to know. So our final goal is to find how to compute numerical flux through this, x equals 0, axis. That is why let's apply the integral form of all equations to this reduced control volume and to this reduced control volume. We now apply the integral form of the conservation loss to the left portion of figure. I mean this one. That is the control volume XL0 times 0t. We apply it here one more time. And here we obtain this object F0L. So F, so it should be capital, is the flux along the t-axis. And we can find it, it's this flux through this H. And we can do the same thing, but for the control volume 0xr times 0t. And we can obtain the numerical flux through this H from right hand side. And if you combine these two formulas, we will get this consistency equation. So the equality F0L equals F0R results in the consistency condition. So that's, intuitively valued condition that the numerical flux computed using different approaches through the same H should be, continuous. And we need to know how to compute this numerical flux, F0L. So that's maybe a bit, actually it's not difficult, but for sure, maybe you need some time to understand on this mathematics, arithmetics. I will show you just in a few minutes the results and you'll understand, so what does it mean. But anyway, so now we're almost here. So we have these two states, UR, UL, this SR and SL as bounding characteristics, and this UHLL state. So we just found it. So it's some integral average state. And so Harten-Lax-van Leer, they put forward the following approximate Riemann solver based on following states. So once again, like in Godunov method and like in Riemann solver, we should consider this array x over t, and we should find the region in which it falls in. So if x over t is less than SL, we should take the left state. If x over t is between SL and SR, we should take this computed constant UHLL state. And if xt over t is greater than SR, we should take the right state. So where UHL is the constant state vector given at the speeds of SR and SR are assumed to be known. And if we define this, all these states, we can now put them into the formula for F0L or F0R, doesn't so matter. Put it here and compute this integral. And on this way, you will get the final result, HLL numerical flux. So if SL is greater than 0, SL is this characteristic. So it's greater than 0. It means that the whole picture is in the region x is greater than 0. Your H corresponds to the left state, and you should take just Fm, where Fm as small f of um. So you should take the left state, parameters in the left cell. So if SR is less than 0, so it means that your full this picture in the region X is less than 0, you should take the right state. But if SL is less than 0 and SR is greater than 0, so this is the most common case, you're something in between, and you should take this formula which follows from, so if you put this UHLL state and UHLL is defined by this formula, you should put it here and easily obtain that you should use this formula. And this formula actually is very simple. So once again, so you have so now we can think of it as a computational cell. You have the left parameters, right parameters, they are UM and UM plus 1, and you compute the fluxes F using these parameters, and you know, for example, the estimates for SL and SR, and so this is a very simple formula, just one explicit formula. So you do not need to do any iterations and compute the product of different matrices, and so no, just this very simple formula. And this is the attractiveness of this approach. And I think we should we still have some time, okay? And the last issue here, we need to know the estimations for wave speeds SL and SR. And as I told, it was, for example, made in work of Davis, and he suggested the simple estimates. SL is just UL minus AL and UR plus UR, and you can compute the minimum for these two values. So you can compute this for the left cell and right cell and take minimum, and it will be SL. And you compute maximum between two cells, it will be SR. Toro believes that these estimates make use the data values only, so they're not recommended. Actually, they works. Actually, usually in my simulations, I also add the comparison with 0, and so they works. It's possible to use another approach. You can use the estimation SL equals U tilde minus A tilde, where U and A are raw average particle and sound speed velocities. So as I told to you, these raw speed averaging procedures, they are used not only for computing these averages here in matrices. So we discussed this raw method, and I told to you that, for example, if you take these, compute these matrices for raw averaging, you will get the raw approach. But actually, these averaging procedures can be used as part of different numerical algorithms, and then this is the example. For example, you can compute the estimations for these speeds using raw averaging, or other approaches. And so that's also a thing I'd like to stress, that what does it mean today to develop a new method? So fortunately or fortunately, the Godunov method can be invented only one time, and it has already been invented and developed. But what should we do now? What should we do with that? So how can we contribute to the development of the numerical methods? But reality is that, in numerical methods, the majority of them, they are not just, solid methods. There are different parts, and depending on the problem, you can try to contribute in different parts of these numerical methods. For example, just as an example. So for sure, this framework of the HLL method, so it exists and we understand it. But depending on the problems in the consideration, you can propose different choices for this SL and SR. And for some problems, one set of SL and SR will work better than another. And that's the idea. The next important and very, so I think this is also one of the most important part of course when you try to establish the relationship between different parts of the course, relation to other methods. So it turns out that this HLL method can be interpreted as, this formula I have shown to you, corresponding to Courant-Dixon-Rees generalization for nonlinear schemes. So it turns out that if you choose SL equals minus S plus and SR equals S plus, where S plus, for example, can be chosen like this one, you will get the Rosanov-flux. And I told you that Rosanov-flux, you can obtain it from Courant-Dixon-Rees with the appropriate choice of this, products of matrices. So you can see that in this case, your numerical flux looks like the flux introduced by Van Leer. So we have already discussed it, right? Or you can suggest another choice for S plus, and you will get Lax-Friedrichs numerical flux. This one. So if you choose in some specific manner these velocities of disturbances propagation, you will get the known formulas that can be obtained using characteristic analysis of order equations. So it demonstrates the strong, coupling and relationship between all these methods. So you can consider. You can develop your method using characteristic analysis of equations, or using this state analysis. But if everything is okay and you think a little about that, you can finally establish the connections between all these things. And actually, in many cases, they're just the same things. For example, like here, Usane flux and Lax-Friedrich flux, and they can be obtained from HLL method with the appropriate choice of velocity propagation. The most interesting part of the lecture, the examples. So in Toro book, for example, you can find a set of test cases that are widely used for validation of numerical methods. The test number 0 is a SOTS test, or SOTS shock tube. And generally speaking, if you want to start validation your approach, you should use these test cases. Test case number 1 here is so-called modified SOT test. The modification is due to velocity to the left of discontinuity. So in the original SOTS test, you have velocity to the left equals to 0, so 0 and 0, but now you have the velocity. And this test is known because here you can see the refraction shock for numerical methods that entropy that do not meet the requirement of that are not entropy satisfying. I mean, the second test is two refraction waves and the stationary contact discontinuity. So it's two refractions, almost a vacuum in the contact region, difficulty in finding pressure at the contact discontinuity. So here you have the velocity UL minus 2 and UR2. So it means that we try to expand our gas, and in the center we will get the strong expansion. And so this problem is called problem 1, 2, 3. So 1, 2, 3 because it was introduced in this paper by Enfield, and he just chose the velocity, density, and pressure like 1, 2, 3 or something like that. So just the specific values of parameters, and so it's known like problem 1, 2, 3 nowadays. So actually, Enfield proposed the method called HLLE. And so actually, you should understand that I explained to you only some general framework, and there are many other further developments of HLL, HLLC, so a lot of methods. So, but I provided you some only general information. The third test, very strong shock wave. Mach number is 198. So in the third test, you have the huge gap in pressure. So PL equals 1000 and PR equals 100. So the gap is 10 to 5. And that's why you have a very strong shock wave. And so it's how to check the robustness of your, such strong robustness of your numerical method. The fourth test, 3 strong right moving discontinuities. So once again, in principle, you can have all waves propagating to one side, but relative to contact surface, the right and left wave should propagate to different directions. So in fourth case, you have 2 shock waves and contact discontinuity, and they all move to one side. The fifth test is stationary contact discontinuity with right moving shock wave and left moving refraction wave. So it's possible to construct a test in which you will have a moving shock wave and moving refraction wave, but contact discontinuity will be stationary. And the sixth and seventh tests, they are stationary isolated contact discontinuity and slowly moving isolated contact discontinuity. So stationary isolated contact discontinuity is when we have just two gases with the same pressure and 0 velocity. and of this contact surface within the Euler equations, it should just be stable, just have the zero velocity, and nothing should happen with that. And so numerical method will either smear it or keep the contact discontinuity sharp. And the seventh test is just the same, but this discontinuity will move slowly. And for many methods, it is known, advantages, disadvantages, and so I recommend you to. So, for example, if you use your software, OpenFarm or Fluent, just ask yourself: so, can I, check all these tests? Is my software able to compute it? And what parameters, what time step should I choose to do that? So it can be very useful. And actually, it's necessary to do that. Now, I'd like to explain you properties of the HLL, and after that, we will introduce HLLC scheme on the example of these test cases. Consider the test number 1, modified search shock tube test. Here is the distributions of density and pressure, and I'd like to compare Godunov method and HLL method. So as I told to you, the initial discontinuity was here at x equals 0.3, and it is known that initial discontinuity, it will be inside this rarefaction wave, and this is a sort of rarefaction shock. So although Godunov method is theoretically entropy satisfying, at the numerical level you can have such problem, and at the same time, yes, you can see some feature at the same point in HLL, but actually it works better. And compare, for example, the shock wave. So this is a shock wave. You can see that Godunov method smears it at 1, 2, 3, about 4 cells, and HLL just the same. Actually, the smearing of contact surface is almost the same, and just the same for pressure. And looking at this picture, you can say, wow, so we developed an excellent approximate Godunov solver. So we do not need any iterations. We can use just, compute just one, some average state, and use it and obtain the results that are, not worse, but actually better than results using Godunov method. But it was not accidentally that I mentioned 7 tests, right? So yes, just for one, maybe your numerical method can be better or not worse than other methods, but you should consider another test cases. As for another test cases, okay, before another, okay, I can show you another. Okay, for example, this is another. I did not change this now. This is the Godunov method and HLL method. Stationary quantity discontinuity. So consider the six test case. So if you do that, you will see the following result. So maybe surprisingly, maybe not. Actually not. I will explain to you why is it so. You can see that pressure distributions in simulation using HLL and Godunov, they are just the same, almost the same. But if you consider the density distribution, you will see that. So this is a shock wave, parameters behind the shock wave, and the contact discontinuity. So Godunov method works well here. And as for HLL, you can see the smearing of this contact discontinuity. And actually, you do not have this plateau behind the shock wave at all. And so the amplitude, it should be about 6, and here is about 4. You have tenths of percentage of error in predicting these parameters behind the shock wave. So as I told, as we expected, we do not have this wave, contact wave at all in our HLL test. It means that in case where the consideration of this contact wave is important, the HLL produces, huge error. So it's not recommended to be used in problems where you're interested in the behavior of contact surface. So contact surface, for sure, if we're talking about just gas, it's surface between 2 different gases. But actually, and I will show to you, you can use HLL type methods for multi-fluid, multi-phase flows, in which the interface can be not only between just gases, but between gas and solid phase, between gas and fluid. And the problem is that HLL method smears all these boundaries that should be, very sharp, actually ideal from physical point of view, if you use shock capture and diffuse interface methods. And for sure, you can take more accurate computational mesh, and the result will be better and better. But anyway, you can see obviously that no, HLL is not, better. Is not better than Godunov method. Anyway, you can see that, for example, shock wave is described perfectly. Why is it so? We need this consideration for developed in the HLLC method. First of all, let's just remind. So we have the Rankin-Hugoniot jump conditions, right? So in gas, the solutions, so all the equations admit the solution in the form of propagating discontinuity, and we derived this so-called Rankin-Hugoniot jump conditions. They're component-wise, so the parameters with 0 correspond to parameters before the shock wave, and with 1, after the shock wave, behind the shock wave. And this is mass conservation law, momentum conservation law, and energy conservation law. And I told to you that so it's possible to rewrite these equations in the following form, using vector form. Right? Why is it so? For example, consider this first equation. Rho1 Vy minus d, where d is the velocity of discontinuity propagation. Let's expand the parentheses here to the left and to the right, and then collect the terms with v in the left-hand side and with d in the right-hand side, and then factor out d, and we'll get this equation. And if you introduce conservative variables vector and flux vector, you can easily see that indeed this is the component of flux vector rho v, and this is component of conservative variables vector, and this is d. So this is just illustration that this formula, generally speaking, this formula is valid. So once again, you can rewrite your Rankin-Hugoniot jump conditions in this form. And highly likely, if you take any book, you will see the Rankin-Hugoniot jump conditions in this form. So in the Russian books, usually people write this form, and in English people using always use this one. Anyway, it's just the same. That this form is useful for us now at the moment. Why is it so? Let's rewrite our HLL scheme. So one of the interpretation of the HLL numerical flux. We got this formula for numerical flux HLL using the integral form of Euler equation and applied it to this control volume, right? And this was a flux through the boundary x0. And we expressed it and put our UHLL here. So that was way how we obtained the HLL numerical flux. And okay, and now we can just rewrite our formula. So we put it here, keep it this UHLL, and then it can be shown that FHLL minus FMN equals to this different times SL. So, and this formula is just the same as this one. So it can be shown that the HLL flux is obtained by applying the Rankin-Hugoniot conditions across the left or right wave. So one of the interpretation of HLL is that we consider this characteristic as a shock wave and apply Rankin-Hugoniot jump conditions. And so this HLL state is built in such a manner that it's valid. So it means that if in your real problem, you have the shock wave indeed, because here we do not specify what is it. Is it either a shock wave or a refraction wave? But if you have a shock wave, like in this case, you will get very good description, because indeed the Rankin-Hugoniot jump condition is included in your numerical scheme. So it does not mean that all the waves will be shock waves. No. So it's just the interpretation. As you can see, it provides also refraction waves. That's okay. But if you have a shock wave, it provides excellent results because so this is one of the interpretations. That is why, once again, so in different test cases, you can get different results and quality of description of different structures. So, for example, some structures of your flow are described well, and in other structures of the same flow, you have poor description of the structures. So it all depends on your numerical method. So, and this is the cons, right? So disadvantages of this method. And we need to fix it, right? How to, so among the advantages of the HLL method is the simplicity for sure. This is just final formula. So it's very easy. If you know the estimations for SR and the cell, so if you chose them somehow, the formula is very simple. And also it's very attractive because you know all these estimates are based only on the speed of sound. So it means that even, for example, if you have a complex equation of state, I told you that one of the disadvantages of Godunov method is that it cannot be applied straightforward to situations when you have complex equation of state. Here, for example, you need only to know speed of sound. So if you may have maybe a very complex equation of state, but if you have some subroutine to compute the speed of sound, that's okay, that's enough for you. So you do not need the expression for the development for internal energy of pressure and so on. You need only speed of sound. So if somebody can provide you the expression for speed and sound under current conditions, that's okay, it's enough for you. So this is a robust method that can be used for, you know, in different situations. And so if you need to obtain something, right, maybe not accurate, but some result, you can use this HLL. You can obtain smeared solutions, maybe with you know, bad resolution of contact surface, but you will get something. What? That is why. So this is this method is useful for that. But if you want to get more accurate description, you should use so-called HLLC method. The idea of the Harten-Lax-van Leer-Contact method. So HLLC means Harten-Lax-van Leer-Contact. So it's the HLL method, but with the resolution of contact discontinuity. So this is the two-wave approximation of the structure of the exact solution of the Riemann problem. And this is a three-wave approximation of the structure of the exact solution of the Riemann problem. So let's add contact discontinuity, contact wave in our solution, and two states, U star L and U star R. This consideration was carried out in a paper by Toro with co-authors in Shockwave Journal in 1994. And actually, you can find this paper, you can check. Actually, I screenshot this, made a screenshot several years ago to illustrate that this paper has more than 1,000 citations. So in our field, that is not very, you know, maybe not very attractive to young people. It's not, it's not very popular and so on, although it's very important. Such number of citations is so it's huge. For example, if your research is about biotechnology or something like that, maybe you can get such number of citations in a couple of months, but not for papers in CFD and numerical methods. And nowadays, so the number of citations should be much bigger. But I'd like to mention that the problem here is that, for example, when you write, so I use the Newton's third law. You do not put a reference to from where you took the Newton's law, right? Because it's belief a common knowledge. So in such a manner, if you write, I use a Godunov method, usually you do not put a reference now, and for HLLC the same. So this method now is just a standard, and although it was published not in 17th or 18th century, it was published just several years ago actually. People often just do not put you know, references and do not cite this paper because it's believed that it's some common knowledge. But actually it was introduced here in this paper. What's the idea? The idea is follows: transition from HLL to HLC. So we have this formula for integral average of the exact solution of the Riemann problem between the slowest and fastest waves at time t. So we obtained this integral average, right? So it was in HL at the beginning of lecture for HLL, UHLL. Now we should introduce the contact wave. And if we introduce the contact wave, now this integral can be subdivided into two parts. So now we have an integral not from TSL to TSR, but from TSL to TS star here, and from TS star to TSR here. That's obvious. And then we should introduce this integral. It's called U star L, is the constant state here between SL and S star characteristics, and U star R is a constant state vector between SR and S star. Okay. Now let's introduce, so in HLL we introduce U tilde with three states, UL, UR, and here we had UHLL, right? Between SL and SR. Now we have S star, we have two states, U star L and U star R. And just in the same manner for HLLC flux. For HLL we had only one part here, and now we have two parts, because we have two states, because we introduced the contact discontinuity. So the problem here is to find unknown values. We do not know S star, so suppose we have the estimations for SR, SL. They can be just the same as previously. So we know UL, we know UR, we know FL, we know FR, we know estimates for SL and SR. We do not know S star and these states, U star L and U star R. We don't know them. We should find them somehow. How can we do that? As I told to you, for HLL, so the method can be interpreted as the application of Rankin-Hugoniot jump conditions across SL and SR. Here, just the same. We can apply the Rankin-Hugoniot conditions across each of the waves. So we can apply it here across the wave SR, across the wave S star, and across the wave SL. So that is why, so once again, Rankin-Hugoniot jump conditions are important. So the mechanics of shock waves is beautiful and important. It's one point of view. Another point of view is that these jump conditions are used widely in the development of the numerical methods, because you should be able to compute correctly all these waves. That's why this Rankin-Hugoniot jump condition should be inside your numerical methods. So this is Rankin-Hugoniot jump conditions for this wave, and for this wave. But now we should work with component-wise notation, because so this vector notation is not enough for us. For sure, so S star is a velocity of contact discontinuity. As soon as it's contact discontinuity, it should be contact discontinuity. It means that the pressure should be continuous across the discontinuity, and velocity should be continuous. So I'd like to remind you that when we analyzed jump conditions, we discussed that there are two types of jump conditions: with mass flow through this jump and without. So the discontinuities without mass flow through it, they're called contact discontinuities. And immediately, if you say that V minus D equals 0, you will get that the velocities should be continuous, and the pressure should be continuous as well across this contact discontinuity. So this is the first requirement, and the second requirement. So no, that's enough. Consider, for example, if our yeah, I think this maybe no, that's okay. Yeah, consider the relations for the right and left waves. So we consider this one for the left wave and this one for the right wave. And again, we expand the parentheses and move some guys to another part of the equation. Then we should use component-wise notation. It means that we should remember that this is the conservative variables vector, this is flux vector for the left wave and the first two components. So consider, for example, left wave, this one, blue, and just say that for the first component of U star L is rho, and the first component of S is rho V, and so on. That is why it will be SL rho minus rho S, because it should be rho V, but V equals S. We take it into account. SL rho L, because it's the first component, minus rho L VL. So this is the first component of this equation, and then this is the second component of this equation. Once again, I just try to explain to you. This is SL, and the second component of this guy, and the second component is rho V, but the velocity equals to S star. So just very formal, application of this formula, just expand it for each component. Then the idea is that we want to exclude rho star L. That is why we factor out SL here, not SL, S star here, and we multiply both sides of this equation by S star, and then we express it here, put it here, just some arithmetics, not very difficult, but anyway. And on this way we obtained the relationship between P star and S star. Actually, it looks like, so as you can remember last lecture, how did we solve the Riemann problem? We considered the right wave and the left wave, and we got the relationship P, the relationship in terms of P and V, velocity and pressure for right wave and for left wave, and then we expressed the velocity and said that at the contact discontinuity, velocity should be the same, should be continuous, and obtain the solution. Here just the same. So we consider the left wave, and this is relationship between P star and V star. Then we should consider another wave and say that the actually pressure should be the same across the contact surface S star. Similarly, for the right wave, we have this expression. Then we can say that this pressure should be the same. So from equations 1 and 2, we obtain the velocity S star. So it depends only on known variables, on pressures and velocities to the left and to the right of discontinuity, and on these velocities SL and SR. So you can find these formulas in numerous papers and books. Actually, here I'd like to show you how to derive them. So that's simple, and there are a lot of connections with the consideration of Riemann problem and so on. But actually, so that's not an obvious thing. So nobody can guarantee you that using in such a manner you will get a workable method before you will do it and try to use it for simulations. And that's the genius of the authors of this method. Feel all these things and propose working approaches. Because for example, for HLL method, so we obtain this state UHLL. And you may think that, okay, if you know this state UHLL, maybe we can just take it and put it into the flux. And FHLL compute not in such a manner as just like F of UHLL, like Godunov-flux. Maybe, so this would be a valid approach, but no. If you will do that, the scheme will not work, because it should be built on integral representation and so on. So I mean that all these things are not obvious, and there are different ways how to do that. And I explained to you the approaches that really work. And that's it. So we obtained the formula for the velocity of contact discontinuity, and this is the formula for HLLC flux. So if you know S star, we know everything else, and you can check that these states. So once again, the problem was that we do not know these states. So this is the HLLC numerical flux, and we need to know F star L here and F star R here. And in the dependence of, depending on the signs of these speeds, we should take one or another state. So if you know F star, it's possible to compute all our things. And the flux will look like this one. It's a bit difficult maybe, but actually no. So everything is known here, just arithmetics. And now we can compare the results obtained using Godunov method, HLL method, and HLLC method. So these two pictures I have already shown to you that HLLC fails to resolve the contact discontinuity, but HLLC produces excellent results, maybe even better than Godunov here, because the plateau here is better than here. But as for example, pressure and the description of the shock wave, they are still all the same. Because again, in HLLC method also, as well, we have the Reinke-Hugoniot jump conditions as the foundation of the development of this method. That is why the shock waves are described perfectly well. And this is the 7th and 6th and 7th test case from the table I've shown to you. So this is the stationary contact discontinuity. So it means that you have this contact discontinuity, and the exact solution is that it should be at the same position in time. And the HLLC method, it smears this contact discontinuity. So in time it becomes more smeared and smeared. And the HLLC just keep it very sharp. Not very sharp, but ideally sharp. It does not smear at all the stationary contact discontinuity. As for slowly moving contact discontinuity, HLL method works in the same manner. It smears this contact discontinuity. HLLC method also smears moving discontinuity, but significantly less. So the resolution is much better. So you can compare this one, and so you can see here it was stable, and here in time it moves. So right, it changes its position. And for moving contact discontinuity, you have some smearing using HLLC method, but anyway, the result is much better in comparison with HLLC method. Okay, I have some time for the last illustration. So as I told to you, so that was about gas, right? But I told to you that these methods can be applied for much more complex problems. For example, multi-physics problems, multi-fluid, multi-phase flows. So one of the problems that I solved was the high-speed impact of metal plates. So there is a process called explosive welding. For example, in HIT we have the State Key Laboratory of Explosive Welding. So it's a way how to get the materials with different properties. For example, if you have plate of one metal and it is stationary, and you have plate from another metal and it is impacted with a huge velocity because it is thrown using explosive charge under some angle, and so they interact, and there is sort of mixing at the surface between the plates, and you get the specimen with the specified properties. For example, the lower part has one properties and the upper part has another properties because they're from different metals. So this process is called explosive welding. And if you after that cut this specimen, you will see that at the interface boundaries there is a sort of hydrodynamic instability. So because at the moment of impact with huge velocity of several hundreds meters per second, the metals behave like pseudo fluids, and you obtain the sort of instability at the interface boundary. It produces this process of welding. So and for sure it was computed for ages, and I was interested in development of model how to compute such sort of problems using shock capturing approach. So if you use Lagrangian approach, it's possible to consider the problem of impact, yes, but not the development of instability. It's much more difficult. But the idea was how to apply the model for shock capturing simulation of this problem without consideration the interface boundaries. So this is the physical statement of the problem. So we have a steel plate and we have a lead plate, and the lead plate is thrown, impacts the steel plate with velocity 500 meters per second. And the steel plate has three boundaries. So here's air, and here's air. So suppose the problem that the lead plate with 2 millimeters thickness, so it impacts the steel plate several millimeters thickness as well. And due to high speed velocities, so both materials, so actually they're metals, you can see the densities, right? Here's density of air and here's the density of steel, but they behave as compressible medium. And how can we describe this? So this model is called so-called Baron-Rosati equations. So this is the example of hyperbolic equations of multiphase theory. So this is an example of very complex hyperbolic model. So one of the important things that this model is hyperbolic. Actually, you can understand it. So this model comprises mass, momentum, and energy equation for air, mass, momentum, and energy equation for steel, mass, momentum, and energy equation for lead, and you also need to add some more equations because alpha is the volume fraction of material. So in this model, we believe that each volume contains all materials simultaneously. So each volume contains steel, lead, and air. But if you have pure steel, it means that you have very, very small amount of air. It's more numerical trick or not physically. And this is the, so you can see also this very convenient for us term ut plus fxu, right? But the problem is that this system is not conservative. So it can be written in the conservation form because we have this term h proportional to the derivatives of our variables. And so we didn't discuss it, but there are hyperbolic equations, but not conservative equations. And for such equations, all considerations that we have that we carried out are much more difficult. For example, you're not able to write Franken-Hugonian jump conditions for this in such a manner. So in principle, you should the Riemann problem does not have a unique solution. You need to choose the unique solution. You should provide additional conditions and so on. So even hyperbolic models, they can be much more difficult. So, but anyway, you can see that why our course is about the Euler equations, because even for very complex model, anyway, you still have Euler equations. So the basis is the Euler equations, and then they can be multi-phase models or some additional physics here and so on and so forth. But everything starts with Euler equations. And what I would like to show you just the results and how all the things we discussed are implemented here. So comparison of the HLL dashed and HLLC solid methods. So suppose we have this steel plate, the green line, it's the volume fraction. So when it's 1, it means that the area is occupied by steel, 3 millimeters thickness. And the red part is the lead plate. And the lead plate is so it impacts the steel plate. And the blue curve is pressure curve. And when one plate hits another one, we have strong shock waves. And this shock waves propagates propagate inside these plates. So the arrows indicate the directions of propagation. And the simulations were carried out using HLL method for these equations and HLLC. And for sure, the HLL and HLLC methods for older equations, they cannot be straightforward, generalized for much more complex. So there are also difficulties how to write HLL and HLLC methods for these equations. But anyway, it was done. And you can see here how in this more realistic computation, the general features of methods are implemented. For example, so this is the boundary of steel plate, and you can see that in simulation using HLLC method, it is the ideal boundary, results mirroring. At the same time, for HL method, you can see this mirror. So you can imagine that, for example, you have a plate and you put it on the table, and that's it. And before any disturbances, you would like to have the ideal boundary of your plate. But in simulation using HL method, it is sort of you have some diffusion. numerical diffusion, right? And that's it. That's not good. At the same time, or for example, this contact between plates. You can see this, so this region of numerical smearing. At the same time, if you compare profiles of shock waves, you can see that they are almost identical in simulations using HLL and HLLC approach. That's because both are based on Rankin-Shugonian jump conditions. And why do we need to attend such classes and listen to such courses and do the simulations of very simple test cases? Because we will learn a lot of information about that that can be used for interpretation of results of real problem simulations. So if you know that HLL and HLLC simulate, so can produce an excellent predictions for shock waves, like here, you're not surprised to see that the shock waves are here described almost identically using both methods. But at the same time, all contacts, so the simulations using HLL method suffer from smearing, right? And you can see here. Then the shock wave propagates and interacts with the free boundary of this plate, and it reflects in the form of a reflection wave. So it means that you have some compression of your material, and then shock wave switches the free boundary, and you should get the decompression, right, or reflection of your material. And it's carried out in the reflection wave. In the reflection wave, the pressure should go down the initial pressure. And you can see that in HLL method, this is dash curve, you have some, it does not decrease to initial pressure. But at the same time, this blue curve, solid curve, corresponds to a reflection wave in simulation using HLLC method. It's okay. You have the decrease of pressure under initial values. And so the equation was this reflection wave interacted with this contact boundary, and we tried to measure the acceleration of this contact boundary and so on. But from here, I'd like to show you just the comparison of simulation results using these two schemes that we introduced. And I'd like to demonstrate to you that a number of features that can be seen from very simple test cases, they exist in real problem simulations. That is why we should know that.